Very good morning everybody. Today we are going to discuss about Ethernet frames. Like CAN, Ethernet also use the frames to transport the data bits from one ECU to another ECU or one node to another node, right now. So we are going to discuss about that in detail today, because that is the second step in using Ethernet network standard, right now. So all data in Ethernet network travels in a structure called frames. And Ethernet frames as defined fields. As we have number of fields in CAN data packet, we are also having different fields in the Ethernet packet for data and other information to help the data to get its destination and to help the destination computer determine whether the data has arrived intact. Not only the data field that we have in the Ethernet packet, also we have handshaking and error checking fields like CRC, frame sequence. Those things also paired along with that original data. So all these things consist of a frame. Like all these things create a frame right now. So we are going to study the fields in an Ethernet frame in detail in upcoming slide. So what we have to know at this point is Ethernet also using a packet based communication. It uses the frames to communicate the data. The Ethernet controller hardware places the information to be sent in the frame for transmitting and extracts and stores the information in received frame. So it is the responsibility of Ethernet controller hardware to encode your data into the into the Ethernet frames and then convert them into equivalent physical signal. As we have the physical signal in CAN, similar to that we are also having the physical signal in Ethernet. So the exchange happens via these physical signals. The physical signals are similar to the PWM signals. Those who studied CAN with us know about it, what they are and how they used to be. Even in the previous session I explained, I showed you the CRO screenshot. In that we had seen the physical signal. These are the pulses which will be exchanged during the communications. Okay, no? So the converting that your software zeros and ones into a physical signal is done by the controller. At the same time, when you receive the external physical signals, that means if some other ECU transmitting the Ethernet packet, that is also digitized by the Ethernet controller hardware upon reception. Like even it receives it, it digitizes it. After digitizing it, we will extract the data portion from the packet and then we will store it. So this is how the Ethernet communication used to work. It is almost similar to what we saw in the CAN standard. Okay, now then the fields of Ethernet frame. This is typical Ethernet frame that I shown you in the last session also. So what are the fields that we have in Ethernet frames? The preamble is the first field, which is preamble in a startup frame delimiter, nearly some 8 bytes. These 8 bytes says that your packet this is the beginning of your packet, and they bring the attention of other nodes that when you transmit preamble, it means that you are about to transmit. So other will start listen you. So because when the bus is idle, they will think that nothing is transmitted over the line. So they will do their work. The moment you transmit the preamble and then start off frame delimiter, they will come to know that there is something going to happen in the bus. So there will be some thought of transmission. So they will be ready. So it is just like a warming up for reception or reception of the message, or warming up the other nodes to be ready to receive the packet. Okay, no, that is what these two fields. For that only these two fields are used. Then the destination address. Here we deviate. After startup frame, when you go and see the CAN packet, you will have identifier. That means your arbitration field will be there. So here we are having a destination address. as the very in the first place after start of frame delimiter. That means who is going to receive the packet. In the CAN packet, we don't have those sort of information. It is not a node based addressing, absence of node addressing. There is no, the node addresses are not encoded in the packet. That means we do not know who is going to receive the packet if you just monitor that in the bus. Okay, no. So because CAN packet does not have information about the destination address, but in Ethernet that will be there. The physical address of nearly some 6 bytes of physical address of your destination, otherwise receiver, will be encoded in that. After that you will have a source address who is transmitting. So these two things are newly added in the Ethernet. We don't have these two in the CAN. Then the length, even in the length, in case of length in CAN we have DLC. Here they call that as a length as well as or type. So it is 2 byte information. In that we will have in that 2 byte we will encode how many valid bytes we have, how many valid data bytes we have, right? No, if you take CAN standard, OSEC TP standard, the first byte of your CAN frame will be the size of single frame. After that you will have the data, right? No, so similar to that, in the Ethernet we have the length after source address. That will tell you how many valid data that you are going to have in your data field. That is what the thing. So this number, if it is less than or equal to 1500, it is simply a length. It used to have additional information about the type of Ethernet standard that you are using. Like there are something like a TCP IP, UDP. So like that we have different types of doing Ethernet communication. That data will be encoded in this byte. Okay, now as per the standard, it is only 802.3. It is just like initially it was made only for length. Later they added this type information over it. Okay, now so data, so remaining after length you will have data bytes. Your data bytes can be from 46 bytes to 1500 bytes. Why it is starting from 46? Can I have less than 46? No, you can't have. If you have like that, you should pad with the additional bytes and have to make that into 46. So then it is a minimum requirement in the Ethernet packet. You have to maintain that. The maximum you can go up to 1500 byte. If you want to if you have a data which is more than 1500, you will follow the same multi-frame strategy as we have in CAN. Using OSEC TP we are able to transmit multi-frame. Similar to that, the Ethernet allows you to transmit multi-frames, multiple Ethernet frames. Then frame check sequence. In CAN packets we have CRC, here we have frames, we have that in a different name, that's it. But the method of calculating the frame check sequence or in a CRC in the CAN, no, both are same. They use some sort of algorithm that is applied over the data bits, then they will come up with the number. Here it is 4 byte number, there it is 15 bits number. So then that 4 byte number is encoded in the packet itself. Those who studied CAN with us know about it. Like while transmitting, they encode, they calculate, they and then they transmit. On the receiving end, they compute their own that is, they are also computing the same CRC using same algorithm that was used by the transmitter, and then they compare. If the computed CRC by the receiver and the received CRC from the transmitters are matching, then they will accept the packet. Otherwise they will not accept the packet. This is how the Ethernet communication works. These are the important fields. What are those? Preamble, start of frame delimiter, destination address, source address, length or type, data, and then the frame check sequence. These are the fields that we have to remember. Here we don't have like error frames, those sort of things, overload frames as we have in the remote frames, as we have in the CAN. here this is we have only one frame structure. Then the preamble because the Ethernet noise is very fast. Using 1 bit for start of frame is not more sensible. We can't differentiate the packets. That's why they are using nearly 8 bytes, I believe. 7 bytes for preamble and 1 byte for start of frame delimiters. So 8 bytes, a fixed pattern. There will be a fixed number, and that will be used as a preamble, and then we have a start of frame delimiter, which is like a separator, which is like a divider between the preamble and the rest of the fields that we have in the Ethernet packet. So along with the preamble and the start of frame delimiter, we create a start of frame initiation. That means we infer other nodes in the network that we are going to do a transmission, because the Ethernet is also using the same concept of CSMA, collision carrier sense multiple access with collision detections. When the carrier is free, only then they can transmit. Till the time, the other nodes in the bus should wait. The moment the bus is free, everybody has a right to transmit, they will try to transmit. Okay, now how? But in CAN we have a concept of arbitration. We don't have that in the Ethernet. Instead, we have some different methods. Let us see that. So after preamble, you have a destination address. Who is going to receive it? Every Ethernet interface has 48-bit physical or hardware address that identify interfaces on the network. So every node should have a physical address. Destination address field contain a physical address of the intended receiver of the frame. So here the packet is one-to-one, like we are encoding. We encode the information about the destination in the packet itself. But when the packet comes to the network, everybody in the network will know about it. There is a packet. After they have after preamble, they will decode, because that is the destination address is the first one. So they will decode the destination address. If the destination address encoded in the packet doesn't match with their physical address, they will simply consider that it is not for them, so they will ignore it. The receiver may be an individual interface, a group of interface identified by multicast address, or a broadcast address to all interfaces in the network. So in Ethernet communication, we can do three types of things, like one-to-one, a node-to-node transmission of the packet, and then node to group. One node can transmit a packet to group of nodes, and then node to all. That means broadcasting. So every node in the network will receive the packet and they will work on it. So these are the three types. What are those? The one that is a one-to-one, and then multicasting, and then broadcasting. These are the three methods in which the packets are transferred in the Ethernet network. Every interface in the network read the destination address of received frame. If address doesn't match the interface physical address or multicast or broadcast address, the interfaces has been configured to accept. The interface ignore the rest of the frame. That means if every interface has their own, every node has their own physical address. Upon receiving a packet, they will compare the destination address of the packet with their physical address. If there is no match, they will simply ignore that. Source address field contain the 48-bit physical address of the transmitting interface. As we have 48-bit destination address, we also have 48-bit source address. That means we have to say who has transmitted that particular packet. That is also part of packet. Then the length and type. Length bar type field is 16 bits that can have, that means 2 bytes, that can have one of the two meanings. The field can indicate the number of bytes of valid data in the data field or protocol used by the data in the field that follows. That means whether it is a UDP, TCP, those sort of things will be encoded. If the value is less than or equal to 1500 in decimal or 5DCH, the value indicates length. That means if the value is in the range of 0 to 1500, it means that you have only a length in that. Data field must contain between 46 to 1500 byte, that I already told. If there are less than 46 bytes of valid or usable data, the length field can indicate how many bytes are valid. If you have a data which is less than 46 byte, so you have to say in length bit you have to encode how many of them are valid. If the value is greater than or equal to 1536, that means 1000 600 hex, length bar type will indicate the protocol that contents of the data field used. That means, as I told you before, based on which protocol they are transmitting that Ethernet packet, whether it is a TCP or UDP, those things we will discuss about them in detail after some time. As of now, you understand that they are two different flavor of transmitting Ethernet packets. Then the data field. Data field is the information that the transmitting interface want to send. Right now, the data field must be between 46 and 1500 bytes. If there are fewer than 46 bytes of data, field must include pad bytes to increase size to 46 bit. That means usually the padded bytes will be 0. So if that is the case, your length should indicate that how many of them are valid. If the transmitting interface has method. As explained earlier in this chapter, data field often contain additional information besides the raw data being sent. As we told before, we have like frame check sequence and then preambles, all those stuff. They are like vessels. Using that only we can able to transport our original data. Right now, other than the original data, we also have these handshaking fields. That is what they try to mean here. The information is typical. Okay, the data field used to contain sometimes header. The information information about the they used to call that as some header. Like in data field, it used to be encoded. The Ethernet frames doesn't care what is in the data field as long as it meets length requirement. Another term for content of the data field is the message. The data payload or message body is a message minus any header or supplemental information in the data field. Frame with the full 1500 data bytes are most efficient because they have just 26 bytes or less than 2% of overload. That means like at the other extreme, the frame with just 1 byte plus 26 bytes of header and required 45 bytes of padding as 71 bytes of overhead. An Ethernet frame must be at least 512 bits, 64 bytes, not including preamble and start of frame bits. This is like this is the size of frame with a minimum 46 data bytes. Receiving interface ignore the frames that are shorter than this minimum size. If you have data which is minimal then shorter than minimum size, automatically that will be ignored. That means if you transmit it without padding, they are talking about. So with padding, you have to maintain that 46 data bytes. Frame check sequence. The frame check sequence field enables receiving interface to detect the errors in the received frame. The electrical noise or other problems on the network can corrupt the frame's content. A receiving interface can detect the corrupt data by using the 32-bit cyclic redundancy check value in the frame check sequence field. The transmitting interface performs the calculation called the cyclic redundancy check on the bytes to be sent and place the results in the frame check sequence field. Receiving interface perform the same calculation on the receive byte. If the result matches, frame contents are almost certain to be identical to what was sent. Ethernet controller's hardware typically performs the CRC calculation on both the ends. On detecting the error in the received frame, the controller typically set the bits in the status bit. So if there is an error, they will set the status bit. So actually that the CRC comparison, no, I used to explain with the diagram with to my students usually. Let me bring that diagram. See, this is, you are transmitting it now. So the preamble is the first one which used to go there. After preamble, we have what we have, destination address and then source address and then your data field. At the end of data field, when you reach, all of them are going serially only, no? So they move out serially from one node to another node. After preamble, then startup frame delimiters, destination address, like that. The moment the receiver receives the last bit of your data, by that time it will be, it has come, by the time it will complete its CRC calculation. How? The moment you send the BF preamble bit now, from that time onwards it will be ready to compute the CRC. As long as it receives bits one by one, it used to compute it. When you send the last bit of CRC and your data bits from the transmitter, by the time the CRC will be, otherwise the calculated CRC by the receiver will be ready. After that, what you have in your field, after last bit of data, you have frame check sequence. That means the transmitted computed CRC will be shifted out serially. So by that time the receiver is ready with its CRC, so it used to compare bit by bit. If both are matching, it will accept the packet, otherwise it will set the status register for the error. So that's how it works. Then the media access control, like in Ethernet network that uses half duplex interfaces, only one interface at a time can transmit. So the interfaces need a way of deciding when it is okay to transmit. So similar to CAN, every nodes in the node in the Ethernet bus, we used to monitor the bus whether the bus is free. When the bus is free, which means that it is in the ideal voltage. When it is ideal voltage, they will try to transmit. If they are transmitting in a different time, there is no problem. If both of them, if every one of them want to transmit, or some two nodes want to transmit at the same time, we have a problem of collision, right? No, even that is applicable in the CAN. So same is applicable here as well. How the collision is handled in the Ethernet is something different from how the collision is handled in the CAN. In CAN, we use the process of arbitration. Here we are not using it. Instead, the moment they detect the collision, the both of them stop their transmission, and then they will wait for a random period of time, then they retry. So the waiting time, no, the retrying time is something different for each node which try to transmit when they do a second try, because if they have a same retry interval, again they will, both of them will retry at the same time, that will lead to collision again. So here they use a different method to avoid the collision. A collision results when two interfaces in the same collision domain try to transmit at the same time. On detecting the collision, transmitting interface doesn't stop the transmission immediately. The moment they come to know there is a collision, they don't stop it. They complete the transmission of preamble, and then nearly some 64 bits of data they are doing it. Instead of, it continues long enough to be sure that other nodes or transmitting interface have time to detect the collision. Till that time, till others understand, other nodes in the network detect the collision, till that time they used to transmit the bits even after detecting the collision. The transmitting interface that has detected the collision always finishes sending 64 bits, sorry, not bytes, bits of preamble and start of frame. 64 bits mean 8 bytes right now. Preamble itself 7 bits, no, 7 bytes, and 1 bit is your start of frame delimiter, if I am not wrong, right? Now 64 bits. These 64, irrespective of whether the collision happens or not, this preamble and start of frame will be transmitted. After that only we have a issue, because we have a destination address at the next field. So in that case only they are doing it. 64 bits preamble and start of frame delimiter. If these haven't been transmitted yet, following this, interface sends an additional 32 bits called jam signal to then stop transmitting. The transmitter, it transmits the preamble and then the start of frame delimiter. After that, in that time, in between, while transmitting these bits itself, it knows that there is a collision. After that, it won't send the destination address. Instead, it used to send 32 bits of jam signal, and then it used to stop the transmitting. The jam signal is an arbitrary data. It should not be an CR, previous frame CRC value. So other than that, it can be any arbitrary data, random data. Delaying before retransmitting. After an interface stops transmitting due to the collision, next task is deciding when to try again. Two interfaces wait the same amount. If two interfaces wait the same amount of time and then retry, another collision will occur. Instead, the Ethernet standard defines a back-off process where each interface selects a randomly chosen delay time before attempting to retransmit. So before trying to retransmit, they are waiting for a random delay, but it is not same. Both of them will not wait for same time. This reduces the chances that two interfaces will try at the same time. If the first retry results in a collision, the interfaces tries again, randomly selecting a delay of 0, 1, 2, 3 slot times. Each new attempts up to 10 retries they are doing it, selects from the larger range of back of time. So there are a table available in the for back slot timing. So using that, they are choosing the different waiting time. After 16 retries, so how much they are going? 16 retries. After that, they will give up. So they are trying 16 trying to transmit it. Every time when they try to transmit, they encounter a collision, means they will give up and then report the failure via an interrupt, using an interrupt. So like that it used to happen. The delay before trying are multiples of interfaces slot times, which is specified in unit of bit times. For 10 Mbps and fast Ethernet, the slot timing is 512 bits, which works out to 51.2 microsecond at 10 Mbps per second, and which works out to 51.2 microsecond at 10 Mbps and 5.12 microsecond at 100 Mbps. For gigabits internet, slot timing is 4096 bit times or 4.096 microsecond. For first retry, an interface chooses randomly between retrying immediately or waiting one slot time before retrying. So the first retry alone has some option. So retrying immediately or wait one slot time before retrying, like that. This is a block diagram, or what you say, flow diagram. It's not block diagram, flow diagram. This is like how that works, like how the CSMA or CD procedure works in the Ethernet. At the beginning, they are setting the collision number to 0, and then each node monitor the carrier. That means they sense the carrier. If the carrier is idle, they are trying to transmit. Right now, if there is no collision, not at all a problem. So they transmit interframe cap, transmit frame, and there is no collision. It is success. Good, well and good. If the carrier is free and two nodes are trying to transmit, both of them will try and transmit their preamble and then start of frame delimiter. While doing it, they will come to know there is a collision. If there is a collision, then what they will do? Both of them will send a jam signal. They will send a jam signal, and then how many bits it is? 32 bits, if I am not wrong. 32 bits called jam signal. A random data will be sent by every node, every transmitting node, and then they will suspend the transmission and they will increment the collision number. That means the first collision. The limit is not reached because they have to go up to some 10 retry, like 16 retry, right? No, so 16 retry, so the limit is not reached. They will go select a random waiting number, both of them, and then they will wait for backup time. After that, both of them will retry to transmit. If the second time they are able to successfully transmit, because they are waited different timings, in that time there is no collision, means the things will go in a success way and both of them will complete the transmission. If not, they will again they will send a jump signal, increment the counter, like that they used to do. So assume they are doing 16 time, they are retrying, but every time they they ended with collision, means the limit has been reached, so it will be aborted. So they both of them will not transmit. They will they will give up. They won't transmit at all. Here there is no counters, error counter, transmit error counter, receive error counter, error frame. Those things are not there in Ethernet. That we have to understand. Then the physical address. Now let us explore further about the physical address of the Ethernet nodes. To send Ethernet frames on the network, a computer places the physical address on the source address field and places the destination physical address in the destination address field. The physical address has two ports: 24 bits organizationally unique identifier, that is first 3 bytes. Those are defined. You can get it after you registering it with the manufacturer, can register with the IEEE and he can get that. The remaining 3 bytes are unique to the hardware. They are like a serial number or manufacturer running number that he want to give. The first 3 bytes are allocated by after they are registering with the IEEE, and they will get that number. Sometimes there is something one more thing in the Ethernet is an address resolution protocol. Sometimes the sending computer doesn't know the receiving computer physical address. How to learn it? So it can learn that physical address by sending a message called ARP message, like address resolution protocol. So to learn the physical address that correspond to an IP address in a local network, computer can send the broadcast message using the address resolution protocol to update an IP address that correspond to an internet domain name, or sending computer can use the DNS protocol to send request to the domain name server. So they used to send, there will be something called as domain name server. They will send the request to that. He will clarify what is his physical address. That's all, team. Today we studied about Ethernet frame structure and how the media access control works in the Ethernet. We will study more things in the upcoming session. Thank you for your patience to listen this lecture. If you like this video, give a thumbs up and you share this video to your friends to motivate us, right now. So thanks for watching. Let me come up with another good video on Ethernet. Thank you.